All right, thanks. Yeah, so it's a real pleasure to be allowed to tell this story about the first color images, as we call them, from JWST, and you can see some of them down on the table there. Um, it was an incredible honor and a very unique opportunity to be allowed to work on this and to work with this fantastic and dedicated team who made it all happen. It's the best team I've ever worked with, and we'll talk a little bit more about later in the talk how that all came to be. So let me just start with take a word. So a big consideration here is the modern news cycle. Right. So today, news is consumed on a screen, often preferably a small screen, as you can see. And whereas in the past, big news agencies drove the news, today they only seed the news, and the news is really created by the people as they consume it and as they share it. They modify the news in a very organic way, and it propagates through the world in an unpredictable manner, as almost as a chain reaction. And one of the things that means is that, well, one thing, you don't really control it, but also if you try to put something out like the first real products coming out of a fantastic telescope like JWST, you really only have one chance of getting it right. And the consequences of not getting it right can be severe. And so we were very well aware of that. And that was one of the big considerations when we went through the whole process of creating the first images. So the first images really is what's called the early release observations, or EROs. So that is a concept that that happens for most, if not all, general observatories, is that they have this product they put out at toward the end of the commissioning. That is not a science product, actually. I mean, science is not really a fundamental consideration in these. It was a pure outreach product. And it's part of a tiered outreach strategy. When we say tiered, it means that we use sort of a layer cake approach, in which the bottom of the layer is where you try to reach as many people in the world as possible, but at a shallow level of information. And the reason you do that with something that appeals in a visceral way to most people. Right? And so this is where the beautiful color images come out. They have to be of a quality that somebody out there who's not necessarily interested in astronomy can see it and appreciate it as a piece of art or as a beautiful piece of music. And once they get interested in it, that is when they ask questions. What is it that I see? And what is this? And they're encouraged and inspired to look for more information. And that's when we bring them into that second tier of the layer cake. But at a base level, we want to grasp people not with a scientific lecture, but with something that appeals at a very basic human level. So that was our task. This was to be released at the end of JWST commissioning, this 6-month commissioning period. It had to be worthy of a flagship observatory. It cost $10 billion. We had to honor the thousands of people who built JWST. We had to include products from all 4 science instruments and all partners, NASA, ESA, and the Canadian space agencies. And we had to cover all 4 of the original JWST science teams. And finally, of course, we had to reach the world. So one of the things that came up again and again, and in hindsight, is a bit maybe a bit antiquated and quaint, right? But we had to appear above the fold in the New York Times. Right? That was our metric for success. All right. So the way that this was done is, and this was so many years actually, maybe in hindsight, a few more years it was really necessary, but the next observatory, maybe not quite as long. So there was a committee set down. It was called the ERO Selection Committee. The task of this committee was to provide input on the scope of the EROs, or what I mentioned in the past slide, and was also to select the targets. And you can see a list of the various committee members. For example, Antonella is in the audience here. There we go. And a number of other people over the years. I was actually not part of the selection, just part of the next part of this. And you can see on the right-hand side here, this is the early release observations that came out of the Hubble Servicing Mission 4. And one of the things we looked at, of course, was the quality of the Hubble images. And I remember growing up with Hubble images, and they had this special quality about them that maybe it's hard to put your finger on, but they seemed more real than anything we had seen before. And a lot of that design and the way that this was done was created back in the day by Salt LeVay, a space telescope. And I'll go through a little bit more detail later on, components of what goes into that, but that was clearly our inspiration. And so the ERO selection committee started with a long list that Salt had put together of potential targets. I think it was 70, I got in the end. And what do you say, more? Yeah, 100, okay. That the committee went through and prioritized because, as many of you know, JWST can't look at any point in the sky at any given time. We didn't know exactly when these observations would be taken. So we couldn't actually early on decide it has to be this particular target because that depended sensitively and even on the day that we had to observe something, that we could make a prioritized list and work from that in real time at the end of commissioning. And so this is where the implementation team came into play. The implementation team was a team that was put together to be highly multidisciplinary, and they had to work on an incredibly short timelines. This is something that necessitated a very, very effective and precise communication between science writers, graphic artists, scientists, and so on. So a very, very unique opportunity to have this kind of outreach production activity that happens in many cases, but not like in an intense way like this. And this was a fantastic, absolutely dedicated group of people, and you can see them all listed here on the paper that we put out after a few weeks of this, after the release of the early images. So we were under a lot of pressure to get things out. There was a lot of discussion during commissioning on how to conduct JWST communication. Right? One thing you didn't want to do was to be silent through commissioning and have a splash at the end because people would say, what's going on? Is something wrong? So you have to keep up a steady cadence of information. On the other hand, you don't want to put out beautiful color images or even approximating color images before we were ready, because again, we had only one opportunity to really reach the world and at its lowest tier. And so at the end of the day, we got 6 weeks to complete the observations from the time that the first observations could be taken until we had to release the first images. And because we had to cover all the instruments, so most of the science modes, we used double redundancy on everything. So let's say we had to produce a product for the star formation, for example. We had to do 2 of them because, what if one didn't work out? This was really the first time when anybody did anything on real science targets, and we didn't know up front how it would work out. And so we ended up with having to run many parallel teams. Some people would be processing the data, as they came out of the telescope. Visualization teams would be creating the color images, and writers would be writing the contextual text that would go along with the images, and all in parallel. There was no weekends. People were working through the nights, and of course, everything didn't go according to plan. We had we did an exoplanet transit, for example. The first one didn't work out. We had to repeat it, and we had a lot of issues with near-spec multi-shutter array, as I'll show a little bit later. And so at the end of the day, it was a very, very packed schedule. So this was a spreadsheet I made to help the team do this every day. There's a row for every day, and every day we would meet from 9:30 to 11 and work through the schedule and all the kinks here, and the rest of the time the folks would work on it. So this is the schedule as it started out, and this is the last schedule I have on my hard drive. So we were marking things off as green as you went through down the list here, and the very end, I guess, since it was the last one here, I sort of gave up at the last few days. It was when we knew we declared victory and we knew we had a good result. But there was only a couple of days of scheduled margin in this year, and this is normally a lot less than what you ought to have. But you know, it worked out. Here's some pictures from that process. The top left one is an actual picture of reaction of when elements of the team saw the first data for the first time. I believe it is actually there's the image of the Dorados as we see below that they're looking at that point. I look kind of bored because I'd already seen it, so, so I was just showing it. So just the way it worked out is that for security reasons, there was only one person who could download all the data, and so it happened to be me. And so I saw them first, and then we could share them with the team afterwards. The top right one is a still from a PBS documentary where they filmed one of the morning sessions we had where we discussed. And in this case, we're discussing the final color grading of the planetary nebula that you also see on the table there. And then the bottom picture, this is when we're all relaxing and we actually we finished and we delivered the product. And so you see all the elements of the team here, so including folks like I would highlight Joe De Pasquale in the bottom right here, and Elisa Pagan on the top left with the dark hair. Those are the imaging visualization specialists who actually make the color images from the scientific data. All right. So let me talk a little bit about some of the considerations that go into these images. So it is true that it may help that you have a telescope that has very high angular resolution, but it's actually not something that's necessary to make a beautiful image. It's not the angular resolution in the sky. The public will not know what the angular resolution is. It is the number of meaningful beams of pixels across the field that matters. Okay. And in order to get a sense for how much you need to make a truly spectacular images, like Hubble images, the ones we have down there, you can go to look at the sizes of the resolutions of TVs that we get today. Right? And so the reason that we can get TVs up to Ultra HD 8K is because the human mind can actually perceive that. Right? If you wouldn't make bigger ones if you couldn't use that. And so it means that in order to have this good picture, you actually have to reach something like Ultra HD 4K, Ultra HD 8K. So something like 4,000 to 8,000 pixels on the side is what you need. And already here you can see that NearCam can produce this quite efficiently. MIRI is harder. You need a lot more tiles to do this. MIRI starts out at 1,000 by 700 or so, so you're closer to standard definition TV. So you need to make big mosaic. So here's an example of what happens when you go from standard definition to high definition. This is not from JWST, this is from the Herschel observatories. On the left-hand side is their first image, right? It says M51, and you can see standard definition. So I think the general public, not to harp on Herschel, right, but the general public will not see that as a spectacular image. Whereas the right-hand side, the Large Magellanic Cloud, also with Herschel, came much, much later. That is a spectacular image. And the only difference, it's not because Herschel has high spatial resolution, it's just the number of pixels. So you can do this with any observer. Another thing that we always enforce is chromatic order. This is where, when people say, oh, the images here, these are inferred images, so the colors that we see are not real, it's false. I reject that notion. There's a really, really great blog article. It should be a real article. It's written by Robert Hurt, I think, back in 2013. You can Google it. It's excellent. And he describes why you shouldn't call it false color. It's not false color in the sense that we've taken a paintbrush and just put on any color. Infrared colors are just as real as optical colors, actually more infrared colors. And what we do is translate them into a visible part of the spectrum. And in order to do that, we have to enforce that bluer infrared colors are assigned a blue color, and redder infrared colors are assigned a red color. It's what we call chromatic order. So all these images have that enforced within them. And so it means that if you go out and take an image with a different observatory, infrared observatory, like Spitzer, for example, you actually get colors that are kind of similar. Okay. Another thing here that is actually an important consideration is signals and noise and depth uniformity. When you take a scientific image, the requirements for that is not at all the same as what the requirements for public outreach image. This is the reason that it doesn't, not that it never happens, but most scientific data are actually not that great for outreach. This is a reason that we're taking specialized data for outreach. Because scientific images are done in the least possible amount of times. You just get enough signal to noise that you can do a scientific experiment. For outreach images, you want enough signal to noise that you have full depth and dynamic range of your image. And typically that will be signal to noise of 20 per pixel or so. It turns out that, if you think about it, for extended sources, if you get around the same kind of signal to noise with Spitzer as you did with JWST, and the reason for that is that although JWST has a much bigger collecting area than Spitzer, the pixels are much smaller, so the signal to noise per pixel is actually roughly the same. So you can't go out and do a short exposure with JWST and get a good output. You had to spend quite a lot of time integrating things, so the exposure times are longer than what you normally have in the outreach images. Another thing is that NearCam, of course, has these two modules. There's a big gap in the middle, so we had to create our own dither pattern in order to get more uniform depth across the NearCam field. We just did that with a mosaic, but nevertheless, it was an important part of the setup. Another thing, and maybe not everybody agrees with me on this here, but again, think about it. This is not for scientific purposes. It's to bring in the general public. You want to keep the spectral range relatively limited in your image, because if you cover a too wide range, a couple of things will happen. One is that the angular resolution is very different between the short wavelength and long wavelength, but also the physical processes that you trace tend to be very different. And so it means that in your blue channel, you're seeing objects that don't appear at all in your red channel. And so you get these weird primary color things, and it looks unnatural when people view that. And this is a very extreme example here. This is a composite of Hubble and Chandra data, right? They're completely different parts of the spectrum, but it sort of gives you an idea of you sort of looks like you put two completely different images on top of each other. And that can be important for to explain a scientific story, but again, it doesn't bring in the general public, that wow effect necessarily. So we tried to keep actually the spectral range as narrow as possible. That's why most images are either NearCam only or Miri only. A few cases we did mix them, but it usually doesn't work as well. All right, so composition, and this was something that was really close to my heart. As with any photography, you compose your image using some basic rules. For example, this one here, we have the famous cosmic eclipse in NGC 3324. This was composed based on a color contrast, a sharp edge. And the reason that we picked this particular part is just from the position angle that was available at the time that we observed it. It might as well have been different position angle. We would have taken a different part of the bubble. This happened to be the one that overlapped with the Hubble image, but it didn't have to be that way. I'm a big fan of the golden ratio. So this is actually shifted a little bit too, so that the edge of between the photo dissociation region and the pHs and the blue ionized gas here fits that the golden ratio. So that's what we call across in photography is called a leading line. Right? So it's something that the eye will follow across. Right? It's natural. Anybody who looks at that image will be drawn to the crest of the mountains, right? Will follow along. So that's just photographic composition effect. I just want to note another thing here. So of course we have to do spectroscopic products as well. Spectroscopy is never going to reach that bottom tier of people, I don't think. You always have to bring them in with images. This is the reason we did the deep field. Originally, we weren't really supposed to do a deep field in the early release observations, but we did have to make a near spec product here. And so the one we have to the right is our near spec product. We had to do a pre-image to get to that product. And that's where the deep image, the deep field came out of SMAX 0723. Of course, it turns out when you do the calculations, and I did that, I was like, how many hours does it take us to get to the depth of the Hubble Ultra Deep Field? And it's not that many hours, and I was like, I've got to just do that, right? And so that's really how that image came about. I wanted to have also with the spectroscopy on the right, just progression in redshift using the same pattern, right? This was a communication means we used here, is to use the hydrogen line and the oxygen lines here, so we can see the same pattern move across the spectrum. Sorry, we used for that. All right, so that was the first images here. I just want to say a few things about the what came after that. Right? So as I mentioned, we do really need to have dedicated time to do outreach images. We do them in a different way, and so we wanted to make sure that we had a continued release of images through the first year that we had available while folks were doing the science and while the observatories collect science data. And also because the original images that were selected for the EROs were taken out of a Hubble list, it missed some opportunities to do some things that, like if they weren't accessible to Hubble or to the visible at all, and a couple of other opportunities. So you can see the list here that we put in. We wanted to do the pillars of creation just because it's so iconic with Hubble. It was too iconic for the EROs, so we put it in the first year. I'm also going to show you that later. The nearest young stellar region in the Ophiuchus core, that's invisible to Hubble completely. And I noticed that the ice giants, Uranus and Neptune, had not been targeted with NIRCam in the first year, so we wanted to make sure we did that. And this is just a planning image from the proposal we put in of the pillars. All right, I'll wrap this up. This is the Oaf region, taken with Spitzer, one of my favorite regions. And we zoomed in on the core there, and just to show this is the composition we made. It still has the golden ratio. And another rule for photography is 3 is a pleasant number, and so it has a 3 in there, the 3 bright stars on the top. So that was the reason we made that composition. And here the ice giant images. Also just wanted to highlight for this here. There was an idea behind that. Nobody had ever photographed solar system objects in the background of the deep cosmos. Right? And so JWST, because the galaxies in every image, gave us an opportunity to do that, provided that you did it in the right way. So these are set up with a short and a long exposure, and then they're composed afterward. All this moves around really quickly, right? So it is a composition of multiple exposures, but it is a real representation of what the ice giants and moon systems look like superimposed on this deep galactic fields. These are really one of my favorites. I don't know if they reach the bottom tier of the layer cake as much as I'd like, but I really like this. We see our backyard and we see the entire history of the universe in one shot for both the ice giants. How do we do in the end? Well, this is from Piccadilly Circus. You count the number of what we call impressions, right? These are the number of opportunities that people had to view the images, whether it was through social media and news or in other ways. And the first images had 200 billion impressions. Right? So it means that every person on Earth had many opportunities to view these images. It was as big as, I mean, you can't really compare to the moon landings, right? It's a very different time, but I think this was up there. It's up there with the Mars landings, one of the biggest scientific events. And oh yeah, we did make it to the above the fold in New York Times. Not once, but 2 days in a row. So thank you, everybody.